as a group leader for your CA group. If you can't contact your team member, please let me know. Yeah, because when I actually do the assignment that time, so I guess there's some issue because the student can still add and drop the module. So some student may have decided not to continue with this module. And then for this project, it actually can't be done by one student himself. So two students can be quite tight as well because you have other modules that you actually need to take care. And then for those who are working, you have your daytime job as well as your family to take care. So I guess 3 students to work on a single project is actually ideal. If you have any issue with actually identifying contacting your team member, please come down after the lesson. Okay? Yeah, yes? Oh, okay. I have uploaded the PDF. They actually list down all the groups. So there's only one name that's actually highlighted. Yeah, so you can actually see the team leader. Yeah, and then from the canvas itself, you should be able to see the person, and then you can actually email him. And then I think the group leader, if your name is actually appointed as a group leader, you're not going to get extra mark, but it's actually good to help to get everything organized. So for your second half, you will have another CA. So you have a mini project. So your mini project last year, if it's the same as last year, it will be done in a group, but you have to submit in individual report. So this may be your group for your Part 2 CA. Yeah. Okay. But Part 2 CA lecturer, he will come after the recess week, and then he will actually brief everyone on what he's planned to do. So I can't actually speak on for him. Okay? Any questions? So there's also a question on the CA where you actually try to draw the letter. Okay. Although on the problem sheet itself, I never actually specified that you should use inverse kinematic, but you should use inverse kinematics to have some key point for the letter. So it's definitely a better solution. Okay. And then so this will be our 5th lecture. Sorry, because of the Chinese New Year holiday week, so we actually missed one lecture. We only have 5 lectures for this half. So next week will be the last lecture. I don't think we should have an additional lecture during the recess week. So everybody can take a break during the recess week. But there will be an assignment. It's essentially an online quiz, a take-home assignment. So that one is actually not going to be difficult. So it's essentially a tutorial. So yeah, I'll give you more detail on the take-home assignment. So the take-home assignment, the online quiz will begin end of next week, so that you can actually have the whole recess week to work on the problem. You can have multiple attempts on the problem. Sorry, let me let me silence my phone. Okay. Any questions? Okay. If no questions, we'll start today's lecture. So I'm moving on to. Oh, sorry. So for those who have problem with identifying your group member or connecting to your group member, please come to see me after the lesson. Okay. We continue with the chapter 2 of the lectures. So So in chapter 1, we are actually dealing with kinematics. So so the kinematics meaning that we look at the positions of the n effectors, and then the position of the n effectors in relation to the joint. So for differential kinematics and statistics, we want to know more than we want to do more. We also want to know the speed, the n effector speed, the speed at the n effector, and then the speed at the n effector is actually very much dependent on the speed, on the velocity at the joint. So since the n effector speed, the speed at the n effector is actually depending on the joint, we can actually have a differential relation. We can actually establish a differential relationship to actually relate the velocity of the joint with the velocity at the n effector. So this is today's topic. So before we establish the relationship between the joint velocity and the n effector velocity, we will look at the representations of the linear and angular velocity of the frame attached to a rigid body. So, meaning that for the classical robotic, we are dealing with a rigid body. You attach a frame to the rigid body, to the n effector, and then what happened here is we want to actually look at the linear velocity. So the linear velocity is also known as the translational velocity. And then on the other hand, we also want to look at the angular velocity, which is the rotational velocity. So the study of the linear and angular velocity of a robot manipulator is actually closely related to the Jacobian of the manipulator. So today's topic is essentially on the Jacobian of the manipulator. So we talk about the kinematic modeling of the instantaneous motions. So the word instantaneous motion refers to the rate of change of motion for a time interval which is very small. So meaning that it's almost zero. So a very, very almost zero time interval. So this the instantaneous. It's a definition of the instantaneous. And then with this kinematic modeling itself, we study, we compute the manipulator Jacobian. So the manipulator Jacobian is essentially a study on the joint velocity and the n effector. So next week we'll look at the applications of the manipulator Jacobian in a status environment. So meaning that we're bringing force and torque next week. So for today's lecture, this is the session 1 and 2 are our main focus. So when we talk about the velocity of a position vector, so we have a position vector, and then the velocity of a position vector is essentially the linear velocity of a point in space represented by the position vector. So every time when we say that we are dealing with the velocity of position vector, we are essentially dealing with a point in space represented by the position vector. So if we actually look at the translational velocity, we have a point Q, we have a position vector QB. The B over here implies that this is the Q is actually with reference to frame B. So when we do the differentiation of this position vector, we have BVQ. So the velocity of this Q with reference to frame B. If we do the differentiation dt BQ, the definition of the differentiation will be limit delta t to 0, bqt plus delta t minus bqt divided by delta t. So this is the definition of BVQ. So this is a differentiation of a position vector. So you have to note the frame at which the vector is actually differentiated. So if the Q is not changing in time with reference or with respect to B, so the velocity is actually equal to 0. So when you actually look at this differentiation itself, the first thing that you actually need to look at, you will have to pay attention to the referencing frame. And then when we actually talk about the velocity vector, the velocity character can actually be described in terms of any frame. So the notation will be, for example, BVQA, we refer to A, it will be A dt BQ. And then if I have BVQ, it's essentially the same as BVQ. So position vector, so when you actually look at a vector in this manner, we know that the velocity is essentially a free vector. So a free vector meaning that it's not the point, so it's essentially free. So it can actually move around the space freely. So this is a free vector. So when I have A, B, VQ, so the B, VQ we refer to A, I can actually express them in this form where A, B, R, B, VQ. So since velocity is a free vector. So this is the rotation metric. So this rotation metric will actually tell you that you rotate B, we refer to A. So the linear velocity V will actually essentially describe an attribute of a point. And then we also have angular velocity omega that actually describe an attribute of a body. So we know that the point, what represents a point, what matters to a point is a position, x, y, z. And what really matters to a body is the orientations. So when we actually look at this angular velocity at the time, we know that we're actually looking at the orientations. So the omega will actually describe the rotation motion of a frame. So for example, if we actually look at this diagram, we have this frame A and frame B. So frame A is fixed, and frame B is rotating with an angular velocity A omega B. So this is the axis. So we're going to talk more about this A omega B as we move on. So if the velocity of a point moving relative is essentially will be moved relative to a translation as well as a rotating frame. So if I have two frames, A and B, so this is the fixed frame A, and this is rotating frame B, and then there's a point Q is actually defined with respect to this frame B. So we say that the orientation of frame B is changing in time with respect to frame A. So A omega B is the rotation velocity of B relative to A. So this is definition. And then if I'm given the motion of Q, defined with respect to B, and then given the motion of origin of B with respect to A, I want to find the velocity of Q with respect to A. So meaning that I want to find the velocity of this with respect to A. So when you actually look at this frame here and then, it may actually don't give you link to the physical world. So we'll demonstrate it in an example over here. So for example, in this frame, in this example, we have a train. So a train is moving, and then this train, you attach a frame to this train, which is T, and then a car is also moving. And then the car is actually moving, you attach a frame to the car C, and this is the U is actually the fixed universal frame. So we want to find the velocity of T and C, T and C with respect to the universal frame. So it's the same concept as finding the velocity of Q with respect to A. So if we assume that the U is actually, U attached to the train is traveling at 100 mph, mile per hour, and then the car is traveling at 30 miles per hour. The train is moving faster than the train. So, and both train and car are actually heading in the x direction of U. So they're heading the x direction of U in this manner. So the position of the C origin, with respect to this C, can actually, if you do the differentiation itself, you will have you'll be able to find the velocity of the C origin. So this be moving. So it's actually given over here that the car is moving at 30 miles per hour. So UVC origin is essentially the velocity of your car is actually equal to 30x hex. So meaning that it's actually moving in this direction at 30x hex. The 30x hex actually, the x hex over here gives you the direction. And the 30 is your 30 miles per hour. So what about the T, the train origin, the frame that's actually attached to the train with respect to the car? So both of them are actually moving in the same direction. So what we are interested is a relationship between this frame T and frame C. So the velocity of the frame T and frame C. So your VT origin with respect in terms of frame C is essentially your CVT is your CVRVT. So you know that the velocity is a free vector, and so we can actually simply multiply the rotation metric over here. So you have your CU, R, and then the VT, the speed is 100 in the direction of x, so x hat. So UCR is essentially your UCR invert 100 x hat. Okay? And then, so this is what happened when you have your U Vt, so meaning that your velocity of the train with respect to the u, and with respect to traveling with respect to u, and to reference to c. So what happens is if I'm looking at my Vc origin t with respect to my c. So meaning that if I have my c, my velocity of the car with respect to t, and then in terms of c. So if you do the same as what you have done earlier, you will actually end up with CTR. So CTR T Vc origin. So you know that the Vc origin is UTR 70 x hat. So you actually end up with this UCR minus 1 UTR 70 x hat. Okay. So the purpose of studying this frame and to determine the velocity of Q with respect to A have its practical applications. So if I have so I continue with finding the velocity of Q with respect to A. So I take away the practical example, and then I just simply focus on the frame itself. So now I want to derive the mathematics. I want to generalize it into a mathematic form. So I have two frames. So this is frame A. This is frame A, which is a universal frame, and then you have this moving frame, frame B, and then you have this point Q, BQ over here. The B implies that the point Q is actually accessible with reference to with respect to frame B. So the same point can also be made response to frame A, so it will be AQ. So the AQ will be equal to the APB origin. So this is what we learned in the second lecture, plus the ABRBQ, the rotating matrix, the orientations, the rotating matrix of B multiplied by BQ plus the APB origin. This is the translations. So starting from here, and then we differentiate with respect to time. So you will have your AQ, when you do the differentiation, you will have your AVQ, the velocity of point Q. So the velocity of point Q, the APB origin will be AVB origin. And then if you do the differentiation over here, you will end up with ABR BVQ plus ABR dot BQ. So this ABR dot BQ is a contribution from the rotation motion of frame B. So what we want to say is, we actually want to show that this contribution part, this term is actually equal to A omega B cross ABR BQ. So there are two things that you need to note. So when I have the BBQ will actually be equal to 0. So the velocity of this point Q with reference to this frame B will be equal to 0 because the vector Q is essentially constant with the view from the frame B. And then so you have this rotation metric ABR. So if you look at this rotation metric itself, you will know that this term will be 0 if frame B is not rotating with respect to frame A. So if frame B is not respect to frame A, so this term will actually be equal to 0. So with that, we can determine the rotational velocity. As we mentioned earlier, the linear velocity will describe an entropy of a point. The angular velocity will describe an entropy of a body. So the angular velocity will describe the rotation motion of a frame attached to the body. So it will be represented by the rotational velocity vector. So if I have this single frame B itself, so this is the rotating axis, is A omega B. So this omega B, A omega B is a set of 3 by 1 vector. So the magnitude of the A omega B will actually will be the speed of the rotations. And then the unit vector along this A omega B is known as is instantaneous. So that means at that point in time. So it's essentially your AK axis of the rotations. So we talked about the AK axis of the rotation earlier in the second lecture when we look at all the different representation. So the direction of A omega B will indicate the instantaneous axis of rotation of B relative to A. So bear in mind that over here, for this entire class, we are actually referring to the instantaneous. So those there'll be a part where we actually compare the instantaneous and normal motion. So A omega B will be related to d dt A B R. If the dt meaning that is actually we differentiate with respect to time. So d dt A B R can actually be written as A B R dot. So this is a metric. Dot over here meaning that is a derivative, so it's a velocity. So if you expand it up, you'll be limit delta t to 0, A B R t plus delta t minus A B R t delta t. So if I have frame A, frame B, this is B itself, this is the omega, this will be the angular, this will be the axis for the angular velocity. So if we move, so this is A B R t plus delta t. So if you expand this, it will be A R k delta theta A B R t. So this is a very small rotation occurring at delta t because the delta t is a very small time. The angle of rotation will also be very small. So when you have the angle of rotation very small, you do a Taylor series expansions. So the A B R t plus delta t will be very small, and then your delta theta will actually be equal to delta theta, and then your cosine delta theta will actually be equal to 1. So this delta theta, the delta theta will actually be equal to your theta. So you put everything together, we have this ARK theta. This is the ARK over here is the equivalent angle axis, and K is a unit vector. So the delta theta is very small. So because the delta theta is very small, the Kx, Ky, the V theta will become 0, and then your V theta will actually become 1 minus cosine theta will eventually is actually equal to 0. So all this simplification, with all these simplifications, the lecture is recorded. So no worry, you can refer to the lecture, to a recorded lecture if you miss out anything. Okay? Yeah. So for small delta theta, you will actually end up with 1 minus kz delta theta, ky delta theta, kz delta theta. You will end up with a matrix over here. So if you actually look at this matrix itself, this matrix is actually known as a skewed symmetric matrix. Symmetric matrix meaning that the off-diagonal element will be are having the same value. This is a skewed one because instead of kz delta theta and this kz delta theta, this is minus kz delta theta. So there's a change in the sign. And then this minus what ky delta theta is ky delta theta, kx delta theta is minus kx delta theta. Okay? So this is known as a skewed symmetric matrix. So if you look at the definition of the skewed symmetric matrix, the skewed symmetric matrix is essentially equal to S is equal to R dot R minus 1, R inverse. So meaning that if I have my ISP, the P is a point, so SP is equal to omega cross P for any vector P and omega equal to omega X, omega Y, omega Z transpose. So we'll come back to this again when we look at next week. When we actually look at the statistic representations. So you go on, and then your d delta t a b will be a b r dot, and then we actually expand out, and then so this is the term that we actually look at just now. So if we go on, and then this essentially is actually equal to this. So you have your a b r t. So the delta t is approaching 0. So finally you will actually end up with a matrix over here. So meaning that your ARK delta theta is actually equal to this matrix. And then the diagonal elements are all 0. Follow? Okay, the deviation is actually kind of a bit boring, but if maybe you can go back and then revise it, and then you will be able to see the link in between them. So you have this ABR dot equal to this. So we mentioned before the KZ is essentially the axis. Remember the equivalent axis that we actually talked about in our lecture 2. So you can write them as A omega BZ instead of K. So your A omega B is your A omega BX, Y, and Z, which is your KX theta dot, KY theta dot, KZ theta dot. This is the same as your theta dot K. So if you can simplify it further, so this essentially is a skewed symmetric matrix. The skewed symmetric matrix can also be represented in this manner. So which is your A omega B cross floor, and then followed by a floor. So this is used to represent a skewed symmetric matrix. Okay. So this skewed symmetric matrix is also known as the angular velocity tensor of the A omega B. So a tensor is essentially a metric. So a popular a sensor that all of you have often come across will be the stress tensor. So your stress tensor, so 3-dimension, 3x3 vector. So this is the angular velocity tensor. So the diagonal elements is actually equal to 0, and it will be expressed in this form. So the vector A omega B is also referred to as the instantaneous angular velocity of a frame. It's instantaneous, so at that point in time. So you can actually, the ABR dot can actually be written in this form, where you have your skewed matrix, the angular multiplied by ABR. So you can actually verify that the A B omega B cross B P is any 3x1 vector. So remember all the position vector, we use a column vector to represent it. So it's actually equal to A omega B cross P. So this representation itself makes sense when you actually see the relation between these. Okay? So when you have your A omega B cross B, it's the same as this skewed matrix multiplied by P. Skewed symmetric matrix multiplied by P. So in summary, a moving frame has both linear and angular velocity. Angular velocity is a moving point, linear velocity is a moving point, and angular velocity is actually associated with the rotating frame. So you have a point as well as an orientation. So the linear velocity of a moving frame is the velocity of the origin of the frame. So when we actually look at the car, train example, the angular velocity is referred to the time derivative of the rotating metric that describes the instantaneous orientation of the frame. So this is something that you need to remember. Okay. Any question? So now with the rotation, now with the linear and rotational matrix, velocity representation established, we move on to the next section, which is on the kinematic modeling of the instantaneous motion. So we mentioned earlier that last chapter, in chapter 1, we are focusing on the position and orientation of the endpoint and its relationship with the joint. So with that, we can actually form a kinematic model. We also talk about the inverse kinematics, where when you are given the endpoints, you can also determine the joint angles. So the question here is, when you're actually operating on the robot, you want to control the speed of the end. You may actually want to control the speed at the end effector. You might want to control the speed at the end point. So to control the speed at the end point, you need a coordinated motion at the joint. So the coordinate motion of the joint, meaning that you need to control the velocity at the joint. So to control the velocity of the joint, the first thing that you need to do is you have to start with the forward kinematic model of the robot. So for example, if we consider these 2 degree of freedom planar manipulator, we have talked about this last week. And then from the forward kinematic model itself, you can actually find that the x, theta 1, theta x, the endpoint x, as a function of theta 1, theta 2, so this is the joint angle theta 1, this is the joint angle theta 2, is equal to L1 cosine theta 1 plus L2 cosine theta 1 plus theta 2. And y, which is a function of theta 1 and theta 2, which is equal to L1 sine theta 1, the joint angle theta 1, plus L2 sine theta 1 plus theta 2. So if we can look at the planar, we can do a quick revision. So this is the two-ring RR planar manipulator. You establish the DH notations, and then from the DH notation itself, you can actually establish the forward kinematics. So with the forward kinematics, you can actually observe that. You can actually observe the x and y are essentially equal to these two. So this is the rotation, and then this is the xy. So I'm actually pulling this thing out for here. Okay, which is your xy. So after you have this xy, you do the differentiations. After you did the differentiation, you have the differential form. So differential form meaning that if you did your delta x, So you do your dx, which is your delta x, theta 1, theta 2, divided by theta delta 1, dd1, d theta 1 plus delta x, theta 1, theta 2, d theta 2. You do the same thing for your dy. So the delta x or delta y over here referred to as the partial differentiation. So you can actually combine this thing to the matrix form. So your dx dy is your d bow x. So the bow x over here indicate that this is a vector. A bow small x indicate that this is a vector. So you have your dx equal to your dx dy. So you can see, it's obvious from here that you have this d theta 1 and d theta 2. So this d theta 1, theta 2 can actually be represented as d theta. So d theta, which is a vector of, is a 2 by 1 vector comprising your d theta 1 and d theta 2. And then, so what happened here is we have this partial differential d delta x, delta y, and so on. They will contribute your Jacobian. So your J Jacobian will comprise of your delta x divided by delta theta 1, delta x divided by delta theta 2, delta y divided by delta theta 1, and delta y divided by delta theta 2. So this Jacobian matrix is known as your manipulator Jacobian. Follow? Yeah. So another way of writing so dx can actually be written as v. So this is essentially the velocity, the velocity of the endpoint. So this is a bow v, and then this is the metric capital J, and d theta, the d theta will be your d dot. Okay. So with your d dot and multiply with your Jacobian and your Jacobian matrix, you will be able to find the n effector displacement, which is your v. Okay. So v is equal to j multiplied with d theta dot. Follow? Okay. Okay, so we continue with the 2 degree of freedom panel manipulator. So we need to determine the value of this delta x, delta theta over delta theta 1. So we know that your x theta 1, theta 2 is equal to this. So you do the partial differentiation. So you do a partial differentiation with theta 1. You do the partial differentiation with theta 1, you will have this, and then you do and then you do a differentiation with the other one, you will actually obtain this other thing. So let me see whether I have the equation for that. I don't have the deviation. Okay, so if I have to put everything together, so this is the endpoint xy. So when I do the dx, ex, well, this is the differentiation. So I can, instead of putting xo and y over here, I put xe. So xe and xy and ye will actually specifically, and the e specifically indicate that this is the n effector. So this is a Jacobian matrix. So when you actually do the differentiations of this from here, you will get this. And then if you do a partial differentiation with theta 2, you do this with the partial differentiation of theta 2, you end up with this. Okay? And then you do the partial differentiation of theta 1 of ye, you end up with this. And you do the partial differentiation of ye with theta 2, with delta with theta 2, you will actually end up with this. So this is your Jacobian metric. Okay? So at that particular instant, we can put Q dot equal to theta 1 dot theta 2 dot transpose. So the VE dot is the VE dot, which is the velocity at the end effector, is your SE dot and YE dot. So this is the end effector velocity. So when you actually put them all together itself, you can have dx dt equal to j dq dt, which is your VE equal to j, the Jacobian metric, multiplied by your Q dot. So a lot of time we use Q dot instead of theta, because Q can actually be equal because to be inclusive of the prismatic joints. So those for this example is a revolute joint. So it will be theta 1, theta 2. So Q can be is equal to D. I if it's a prismatic joint is equal to theta I if it's a revolute joint. So the Jacobian will actually determine the velocity relationship between the joint and end effector. So your Jacobian matrix, which is given over here. So this is a planar robot, and then in this case, you have two joints. So one joint 1, joint 2, and then they're essentially a linear motion because the end effector of the manipulator is actually holding on to a point. So I'm not considering the orientation in this case. Okay. So from here itself, we can actually visualize that you have your J1, theta 1, and essentially a straight. You can essentially a straight is essentially a top, and then you have your top from your theta 1 from the first joint, and then your J2 theta 2 is again another top, which is from your theta 2. So the results will be V is equal to J1 theta 1 dot plus J2 theta dot theta 2 dot. Follow? So what happened? So you can imagine this is your arm. So you have your. So this is your arm. So you have your theta 1, the joint 1 here and joint 2 over here, and then you're turning your joint in this manner. What happens if my both joints are actually extended? So meaning that my joint 1, I extended my arm. So if I extended my arm, I will not have the type of flexibility that I have if I'm actually bending my arm. So when I extended my arm, I'm in a situation called singular. So we'll be talking about that later on. So bear in mind that there's actually a difference between a finite and infinitesimal rotations. So meaning that the very small rotation and finite rotations, there's a difference between them. The infinitesimal is actually something that's so small that there's no way to measure it. So this is the definitions of this. So if I have a 3 by 3 rotation metric representing the very small rotation, dx along the x-axis itself, this x along the x-axis itself, I have this rotation matrix. So this is very small. So when this is actually very small, the cosine of 0, which means it's almost 0. So when it's actually almost 0, cosine 0 will actually be 1. So you have a 1 over here. And then when you have your sine a very small angle, almost a zero angle, you will be the angle by itself. So you have this angle over here, and then so this will end up by the angle by itself, and then cosine will actually equal to 1. So you have this rotation matrix equal to this. So for very small rotation about the y and z axis, you essentially get the same form. So if you put them together, if you have a consecutive rotation about the x and y of a very small rotation angle, this is the resultant matrix. So in this case, we actually ignore the higher terms. So you can ignore the higher term because if you have one very small angle multiplied by another small angle, you have an even smaller angle. So you ignore the higher order, and then you actually end up with something like this. So you can check that the Rx of a small angle, of a very small angle, and Ry of a very small angle is essentially the same as if you multiply the Ry of a very small angle with the Rx of a very small angle. So it means that the rotation will not be depending on the order of rotations. So they are commutative. So the rotation matrix of the very small rotation about the x, y, and z itself is given over here. So if you look at this matrix again, this is a skewed symmetric matrix. So we know that the rotation is not important, and then we also know that the infant-stemmer rotations are also additive. So meaning that if you multiply two together, it's the same as when you're actually rotating when you respectively add the small x and the small x prime, small angle x prime, and so on. So you can actually verify them. They actually obey the rules of additive. So the rule of additive will actually mean that the function of the union or sum of two quantities is actually equal to the sum of the functional value of each quantity itself. So this actually implies a linear systems. Okay. Any question? Yep. So these are properties, and then so we say that this can be treated as a vector in a vector field. So you have all the property of a vector. So you have all the property of a vectors, and then the vector itself, the red color one will actually indicate the direction. The direction of the arrow will actually represent the axis of the rotations, and the length will actually representing the magnitude. So this is different from finite rotations. So a finite rotation meaning that if I start with an object, we are frame attached to the object. I have it rotate along the x-axis. So this is rotate along the x-axis by 90 degrees, and then followed by another rotation along the y-axis by 90 degrees. This is the final configurations. If I do the reverse, meaning that I rotate along the x by 90 degrees, followed by rotate along the x 90 degrees, you can actually see that they are not the same. Okay, although their rotation, the sum of their rotation and the sum of the rotation angle is the same, where you have 90 degrees for the x, 90 degrees for the y. So there's a difference between a finite rotation and infinitesimal rotation. Okay. We move on to look at the computation of the manipulator Jacobian. So earlier on, we look at an example where we actually have a panel robot. So a panel robot is have two joints. The panel robot have two joints, and then we focus on the xy, the velocity, the linear the position of the value of the x and y at the n effector. If we generalize it into a 6 degree of freedom robot, you will actually find that the n effector point itself, in addition to the linear translations, which is actually consists of your xe, delta x, the dxe, which is your xe, ye, and ze. So the d over here meaning that is a very small motion, instantaneous motion. So the d over here indicate that this is a very small instantaneous motion. So the first three column, the first three row will indicate the n effector translation vector. So which is your dx e over here. And then you have this d angle e, which is referring to the rotation angle. Okay? So this will actually representing your rotation vector. So the rotation vector, again, you have three values. You have your theta 1, theta 2, and theta 3. So the dp equal dxe and d angle e is essentially your p dot equal to ve omega e. So you can actually write it in this form. So the p dot is again related with the Jacobian matrix. The Jacobian matrix is J Q dot. So your Q dot is Q1 dot to Qn dot. So we use Q to actually represent the joint angle, the joint variable. So it can be a prismatic joint, or it could actually be a revolute joint. So this is n by 1 joint velocity vector. So it generalizes our 2D panel manipulator to a 3D to a general manipulator. So you have this p dot equal to j q dot. So your p dot will actually comprise of ve and omega e, and then your q dot will actually representing the joint variable. So essentially, the Jacobian matrix is a 6 by n matrix. So you have your 6 element here. So you have your 6 element here. Then your q dot over here will be depending on the number of joints that you have. So the j has to be equal to 6 by n. So it has to be 6 by n. So the j have to be 6 by n so that the p dot is equal to j dot, k, q dot can be consistent. So you have the first three row of the j matrix were actually representing your linear velocity. And the last three rows itself will actually define your angular velocity. So each column vector is actually representing the velocity, angular velocity by the corresponding individual joint. So you have your theta 1, theta 2 here. So if you actually refer to the earlier example, your theta 1, you have your theta 1, sorry, Q1, Q2, you have your theta 1 on the first column and theta 2 on your second column, if you refer to the earlier example. But in the earlier example, it's a 2D panel robot, and then we are only dealing with the linear velocity. We are going on to determine the value of to determine the Jacobian matrix. So the first set of the Jacobian matrix that you may need to determine will be the linear VE. So to determine the linear velocity of the n effector, from this matrix itself, we know that the VE is essentially equal to your JL1 multiplied with your Q1 dot. So this is your JL1. And then if you look at your earlier, it's actually you will be multiplied with your Q dot, which is your dot Q1 to Q dot Qn. So your JL1 will be multiplied with your dot Q1. So you multiply with your dot Q1 plus JL2 multiply with your dot Q2 and so on. And the last term will be JLN Q dot N. Qn dot. So if the joint is a prismatic joint, you can the JLI will be the JLI QI dot will actually be equal to your DI dot BI minus 1. So the BI minus 1 is the unit vector along the Z axis of the frame. So meaning that you are actually it will actually be along the joint axis I, expressed with respect to the original frame. And then the QI dot, the DI dot is the scalar joint velocity. So you can actually visualize it in this manner. So if this is happen to be a prismatic joint, it will cause a motion in this manner. And then, so with that you actually with that you have the definition for your JLI. For a revolute joint, so a revolute joint meaning that if this joint is a revolute joint, it will actually rotate the n effector. So it's rotate the composite of the distilled n. The distilled meaning that the far end from length I to n at angular velocity omega I equal to theta I dot bi minus 1. So this is your theta. This is your bi. This is your theta I dot bi minus 1. So this is the axis. This is the rotational, the angular rotations. So you sum out your JLI QI dot will actually be equal to your omega I cross Ri minus 1e. So this is what we have taught earlier. So this is your, so if you actually look at this itself, this is your Ri minus 1e. So basically the joint, the line that is shooting up the joint with the n effector. So this is from the frame OI minus 1 to the n effector, expressed in this form. So if you do the multiplication, the cross multiplication itself, you have your omega I, which is your theta I dot bi minus 1 cross Ri minus 1e. So you actually end up with bi minus 1 cross I minus 1 Ri minus 1e theta I dot. Okay. So if you look at this further, you can see that the angular velocity of the n effector can be expressed as a linear combination of the column vector JAI. So for a prismatic joint, the JAI QI dot is equal to 0. And then for the revolute joint itself, the JAI QI dot is essentially equal to your omega I, which is your BI minus 1 theta I dot. Okay. So in summary, if you actually put everything together, you will find that to determine the JLI and JAI for a prismatic joint, you will the JLI and JAI will actually be equal to your BI minus 1 and 0. So for prismatic joint, there's no rotation, so it's obviously it will be 0. So this is what happened to your panel robot. So it only consists of the linear element. And then for the revolute joint, the JLI will be equal, and JLI will be equal to your BI minus 1 cross RI minus 1 and E, and the JAI will actually be equal to your BI minus 1. So this is your equation 3-3 and equation 3-4. So another way of looking at it is if I have, is to form a 2x2 table in this manner. So for the linear part of the n effector velocity, and then divide the rho into the linear part of the n effector velocity and the rotational part of the n effector velocity. So if you have a prismatic joint, for the linear part of the n effector velocity will be your BI minus 1, which is your BI minus 1, is essentially equal to your the rotation of 0I minus 1 R 0, 0, 1. Okay. And then for revolute joint, for the prismatic joint, the rotation part will always be equal to 0. So it's always equal to 0. Remember the rotation part actually consists of 3 elements, theta x, theta y, and theta z. So you have your 0, 0, 0 over here. Follow? And then for the linear part of the Jacobian matrix, if it's corresponding to the revolute joint, will be BI minus 1 cross RI minus 1 E. So this is essentially your 0, I minus 1 R 0, 0, 1 cross your dn minus the O 0 n d minus 0 I minus 1 d. And then for the rotation part will be your BI minus 1. So your BI minus 1 is your 0 I minus 1 R 0, 0, 1. So if you actually sum up all that I mentioned just now, you will actually end up with a table like that. So you see how we can actually make use of this table to solve, to determine the manipulated Jacobian of the various examples. So bear in mind that the elements of the Jacobian are general functions of the joint displacement. So in a way, in other words, the Jacobian is configuration dependent. Depending on the configuration of your manipulator, you will have a different set of Jacobian. Okay? Okay. I think we take a short break of 15 minutes, and then after that we'll resume the lesson. Sorry. Yeah. Actually, NUS is not that small. So my office is at block E1. So I forget my water bottle. So I go back to my office to pick up my water bottle. And by the time I come here, the break is over. Yeah. Okay. Can I have your attention? Yeah. Okay. Sorry, I couldn't stay around during the break time. If you have any question, please feel free to come to me after the lesson. Okay? Yeah. I go and get my water bottle. Okay. So bear in mind that we are looking at a very small angle. So meaning that the d phi is equal to d phi x, d phi y, d phi z. So referring to the phi over here refers to very small displacement, a very small angle. And then so this is different from the finite rotations. So a finite rotation meaning that the angle is actually at the macroscopic level. Okay, so we do a quick recap before we actually look at some example. So we have this dp equal to dxe d phi e. So the p over here is referred to the n effector vector. So the n effector vector, you can actually represent it as p dot as well. So the xe over here is the linear displacement. So the linear displacement will comprise of the x, y, and z, the xe, ye, and ze. So we have this phi e. The phi e over here refers to the rotation vector. So again, the rotation vector, you have three angles, which is your rotation along x, y, and z. So if you put them together, you can actually break them into two parts. So the top one can be represented as VE, so which is your linear velocity of the n effector, and the lower three can actually be represented as omega e. So the omega e is your rotation vector. So this can be represented as p dot. So your p dot is equal to j q dot. The q dot over here is essentially your joint velocity vector. So the q1 over here refers to joint 1, and then q1 refers to your joint n. The q1 dot meaning that is the velocity of the joint at q1. So q1 can be a revolute joint or a prismatic joint. So they are related by this Jacobian matrix. This Jacobian matrix is known as the manipulator Jacobian. So Jacobian matrix, if you look at the Jacobian matrix, it's actually structured very nicely, where every column is representing a single is related to a single joint. So the first column is related to your Q1, your joint Q1. The second column Q2, and your last column Qn. So same thing. The first three rows of the column is related to your linear VE, linear velocity of the n effector. The last three rows will be related to the angular velocity, which is your omega e. So the whole thing here is, so the subsequent slides, we are looking at how we can actually compute the JL1 and the JLI and JAI. So we want to determine the Jacobian, we want to compute the Jacobian matrix. And the Jacobian matrix will actually be dependent on the joint type, so whether a prismatic joint or revolute joint. And at the same time, a prismatic joint and revolute joint will have these two components, which is the linear velocity and angular velocity. So obviously, we can simplify the matrix further with a prismatic joint. So a prismatic joint will not have rotations. So the last three columns, the last three rows for a prismatic joint will actually be equal to 0. So the focus here will be the JL1. So this is why you have the JL1 QI dot equal to DI dot BI minus 1. And then the relative joint is actually more, it's kind of a bit more complex. So you have it will actually affect your angular rotation. At the same time, it will also affect a linear displacement. So the linear displacement will actually be given by this relationship where your JLI, the Li over here refers to the linear part of the Jacobian matrix, multiplied by Qi dot is equal to your omega I. So your omega I, which is the axis that we actually mentioned in the earlier part of the lecture, cross the position vector. So position vector Ri minus 1e. So essentially, this is a top. That's what we have gone through earlier. And then for the angular part, the omega e will be equal to your JAI A1 QI dot plus JA2 Q2 dot and so on plus JAN Q dot n. So this is the last three column of your this is the angular velocity of your n effector, which is related to the last three row of the Jacobian matrix. So from there itself, you can actually compute that if for prismatic joint itself, it will be equal to 0. For revolute joint, the JAI Q dot I is essentially equal to your omega I. So which is simply your rotation vector. Okay? The angular rotation vector. So which is your omega I. So your omega I is always equal to BI minus 1 QI dot. We can sum them up together. If we sum them up together, we can actually form a table over here. So this table is kind of convenient when you want to determine the Jacobian of a robot manipulator. Okay. So I'm going to illustrate the determination of the manipulator Jacobian using example. So the general approach. So if you actually look at this itself, you will actually find that you will find the 001 over here. So I'm going to explain how is this come about. So the general approach to obtain the BI minus 1 and the RI minus 1e is illustrated over here. So we actually first define a B bar. So we have so this is BI minus 1, which is a prismatic joint. This for revolute joint itself, this is your theta I dot BI minus 1. So this is your position vector Ri minus 1e. They are all with respect to the base frame. So the D bar, so if we have the BI minus 1 is equal to, the BI minus 1 over here is equal to your 01 R Q1 multiply I minus 2 R Q minus 1 B bar. So the B bar over here is the direction of the joint axis I minus 1 with reference to the frame I minus 1. So the joint axis is actually along the I minus 1 axis. So if you actually look at this itself, we know that the BI minus 1 is equal to 0 I minus 1 R B bar. So this is obvious. So this is your B bar. So the B bar over here is essentially equal to, is a column vector of 0, 0, 1. So if you do this multiplication itself, meaning that the BI minus 1 is essentially the third column of 0 I minus 1 R. Okay? So this is why you have your BI minus 1 equal to 0 I minus 1 R 0, 0, 1. So you don't actually need to do the calculation at the multiplication at all. If you look at the matrix itself, the 0, 0, 1 will give you the third column. Okay? Then the next variable that you need to determine, you determine your BI minus 1. the next thing that you need to determine will be your RI minus 1E. So we look at the same manipulator again. So with this manipulator itself, we can compute the Ri minus 1E using the 4x4 homogeneous matrix J minus 1J A Q J. So this is the homogeneous matrix that you have from your forward kinematics. So meaning that every time when you actually want to determine the Jacobian matrix, you have to start from the forward kinematics. So your x, let the both x I minus 1e be the 4x1 augmented vector of I minus 1e. So your x bar is essentially your 0, 0, 0, 1 transpose. So this is essentially, the x bar is a column vector of 0, 0, 0, 1. Okay, so your x I minus 1e will be equal to this multiplied by the x bar. So actually, if you look at this itself, this is essentially, we refer from the origin. This is this part. So this is the position vector from the origin OE to the n effector. And then the next part is the position vector from the origin O to I minus 1. OO to I minus 1. So if you take this one minus this one, you have this one. Simple? Okay, so you take this one minus this one, you got this one. So this is what we need. So once you have determined that, so if you put them all together, you have it's basically your, if you summarize it, if you break it into, if you simplify it, it's essentially your OND minus your OI minus 1D. So once you have your BI minus 1 and I minus 1, you can actually form the matrix. You can determine your Jacobian matrix. We look at a simple example. Sorry. We look at a panel robot example. So we have gone through this example before. This is the kinematic equations of a three-link robot. So if you panel robot, so you have one joint, two joint, and three joint. This is the n effector positions. With the forward kinematic itself, you can actually determine that the x is equal to px py phi, which is equal to this term. So your px py, and then your phi is essentially the angle from there. So if we determine that, so you have, so this is if we do the differentiation, so meaning the s dot, y dot, and q dot, and phi dot, so you do a differentiation of these three elements, one after another. The phi dot itself, which the phi is actually equal to theta 1 plus theta 2 plus theta 3. So the phi dot will be your theta 1 dot plus theta 2 dot plus theta 3 dot. So you put them in the matrix itself, you will have your s dot, y dot, phi dot. This is your matrix multiplied by your theta 1 dot, theta 2 dot, theta 3 dot. So this is your Jacobian matrix. So this Jacobian matrix itself will be your essentially is your delta x divided by delta theta 1 and so on. So if the Jacobian matrix is not singular, you can actually establish a reverse relationship where your q dot is equal to j minus 1 x dot. So this is, so you can actually do the experiment, do the deviation. You can determine the Jacobian for a three-link panel robot. So what about what about a tree? What about a non-planar robot? You look at a non-planar robot, the RR robot. Okay, we have. So there's the a 2D. We look at the RR robot and RR robot, a planar RR robot, and then now we actually look at a general RR robot. But this RR robot is a 3D. It's a 3D. So it comprises of two revolute joints. So this is the first revolute joint. This is the second revolute joint. This is the end effector. This is the end effector point. So with this, you can do your DH notations. You can attach the frame. So after you have attached the frame, you derive the DH parameter table. So after you derive your DH parameter table, the next thing is you want to determine the Jacobian. So you know that for the manipulator Jacobian, the V is equal to J theta dot. So your V over here comprises of X dot, Y dot, J dot, omega X, omega Y, omega Z. So the first three elements is your linear displacement, and then is your linear velocity. The last three elements is your rotational velocity. So you have so from here itself, you know that you look at the two joints. So the first joint is a revolute joint. So a revolute joint, for the linear part, you will make use of this part of the equations, this part of the table, which is your Bi minus 1 cross Ri minus 1 E. So your Bi minus 1 cross Ri minus 1 E is essentially equal to your 0I minus 1 R, 0, 0, 0, the third column of your rotation matrix, cross 0n d minus 0I minus 1 d. So you fill this up. And then the rotational part will be your Bi minus 1. So it's essentially the Bi minus 1. So this is your joint 0. So you will be 0, 0, R, 0, 0, 1. And then after that you move on to your second joint. So a second joint will be 0, 1, R, 0, 0, 1 cross 0, 2, D minus 0, 1, D. And then the rotational part will be your B1. So you have your 0, 1, 0, 1 R, 0, 0, 1. Okay. So multiply with your theta 1 dot, theta 2 dot. So the first thing here is your 0, 0 R. 0, 0 R, you are rotating frame 0 with respect to frame 0. So meaning that you have an identity matrix. So 0, 0 R is your identity matrix. And then your 0, 0 D is 0. So you have, earlier on, you have compute your 0, 2 A from your transformation matrix, and then you actually, for the last, this is the linear displacement over here, this will actually define your 0, 2 T. Okay? So with that, you have your, and then you have your 0, 1 D is a rotation matrix. So this is your typical rotation matrix with respect to theta 1. So, and then your 0, 1 D is essentially your 0, 0, A1. So it's some that you put them all together into the matrix, and then you will actually get the Jacobian matrix. So if you actually look at this Jacobian matrix itself, there are altogether 6 equations. So you have your S dot is equal to the minus A2 S theta 1 C theta 2 C theta 2 theta 1 dot, because you multiply, because you actually multiply with the theta 1 dot over here. And then your S dot will also be equal to this multiply with the theta 2 dot. So you actually end up with this set of equations. from this set of Jacobian equation itself, you can actually deduce the functions of this robot. Okay. So over here, if your omega jack is equal to theta 1 dot, so meaning that the angular velocity at along the jack axis will only be decided by the velocity at your of the theta 1, and not theta 2. Okay. So you know the derivation now. It's quite straightforward using this table. Okay, you have to start with your forward kinematics. So you need to do the DH notations, the matrix transformation, so that you have your D to compute from there. A panel robot it will be simpler. A panel robot you don't have to think about the revolution part. Okay. Okay. So with a panel robot, you only have the linear part that you need to worry about. So even though there's actually a revolute joint. So for the RR robot, which actually comprised of 2 revolute joints, there isn't any prismatic joint. So let's look at a robot. So this is known as a polar coordinate manipulator. So for a polar coordinate manipulator, it has 2 angular and 1 translation. You have two angular and 1 translation. So this is how it's been depicted, how a polar coordinate manipulator is being depicted. So you have your theta 1. You have your theta 1, you have your theta 2, and then you have and then followed by a prismatic joint that actually provide the linear motion. So if you refer to this polar coordinate itself, you have this which is corresponding to your theta 1, and this corresponding to your theta 2, and then after that you have this one more linear displacement. So there are 3 joint displacement over here. So 3 joint displacement will be the theta 1, theta 2, and D3. So this is a polar coordinate manipulator. So before you determine the Jacobian manipulator, you have to work out the forward kinematics. We do a quick revision of the classical notations. So the classical DH notation will actually tell you that you have your AI alpha I, the DI as well as the theta I. So the DI and theta I are representing the joint variable. AI and alpha I refer to the setup, refer to the configuration of your robot. So after you have, so the frames are essentially given. So the next thing here is you can actually form the table, and then with that you can actually, so you will actually end up with a table, with a DH notation table, something like this. So you have your link 1, you have your AI, alpha I, DI as well as your theta I. So in this case, if you look at this axis itself, with the jack O point on top, jack S to this side, the jack 1 is actually towards here. So you can actually determine that the angle is actually you have your AI equal to 0. So because both frames are essentially a 9. So no, I'll upload these slides. I'll upload this. I will scan and then upload onto the canvas. Yep. So after that you work on the alpha. So when you actually work on the alpha, you're actually looking at the angle difference between the Z0 and Z1. So from here itself, you know that it's actually a 90 degree. But it's a minus 90 degree because it's clockwise. So clockwise will be 90, but will be minus 90 degree, counterclockwise positive. So you also determine your LO as well as your theta I. So theta I is obvious. So this is your theta I. So after you have done with the link 1, you work on link 2, and then same thing, and then after that you work on link 3. So when you try to form this table itself, you have to try to have as many elements equal to 0 as possible. You don't want to have too many. So you want to have the minimum representations. So you can. So over here the theta 2 is straightforward, and then the DI, they are essentially a 9. So your DI is actually equal to 0. So your alpha I is 90 and AI is actually equal to 0 because they are 9. So when you attach a frame that time, it may be good to put them on a 9 if possible. So, and then finally, you work on the row number 3. So after you have worked on the row number 3, you know you are given the template for the transformation matrix. So the template for the transformation matrix, Ti minus 1i is given in this form. So with the table, you substitute in the value. So this is your T01 or 01T. They mean the same thing. Or T12 or 12T, they mean the same thing. Or in some cases, you may see. In some cases, you may actually see that it's written. This is the same as 12T. It's also the same as 12. It's also the same as A12. Okay, and then you have your T23. So the T23 is straightforward. So basically, the T23, if you look at it itself, is essentially just a simple prismatic joint. So when you see a simple prismatic joint in this manner, you can simply this is essentially just an identity metric with a D3 in this case along the z-axis. Okay. So you need to be familiar with all this. So once you have all the matrices, all the intermediate matrices lined up, you want to determine the forward kinematics. The forward kinematics will be T03 or 03T equal to T01 multiplied by T12 multiplied by T23. So I mentioned earlier that the T03 is essentially the same when you can actually visualize it as the one of the subscript and the superscript being cancelled off. You multiply them together, you end up with the final matrix given over here. You multiply, and then after that you do the simplification, you end up with the matrix over here. Okay. So after you have your forward kinematics, after you have the kinematic itself, you can you can move on to determine your Jacobian matrix. So when you determine your Jacobian matrix, all expression will actually be expressed in frame 0. So your B0 will be your B0, which is actually the last column of your 0, I minus 1 error. Your BI minus 1 is your 0, I minus 1 error 0, 0, 1. So from your matrix itself, you will be able to determine that this B0 is equal to 0, 0, 1. B1 is the same thing. The last column, the third column of your rotation matrix will be minus x1, c1, 0. The third column of your rotation matrix will be c1x, x1, 2, c2. So this is what we have done earlier when we actually determine the transformation matrix. So bear in mind that the BI vector is determined such that the angular displacement, revolute or linear displacement, is positive in the usual sense, meaning that the counterclockwise positive. So the sign is actually very important when you work it out. So this is your B0, which is 0, 0, 1 along the z-axis. This is your B1, which is your minus sine theta 1, cosine theta 1, 0. And then this is your B2. Okay? So you first determine your B0, B1, and B2. And then after that you have to, and then after that you need to, for the revolute joint, you also need to determine your R I minus 1E. So your theta 1, your R0E will be L0 B0 plus D3 B2. So this cells will actually be equal to this one plus this one. And then this R1E is essentially equal to this one minus this one. So but this one minus this one is essentially your D3 multiplied by your B2. So from here itself, you can actually, your JL1 and JA1 for theta 1, so your JL1 is actually equal to your B0 cross R B0. You are using this because it's a revolute joint. Theta 1 is a revolute joint, and then you are determining the linear part. So you're using this part, which is your B0 cross R0E. And then the angular part will be your B0, will actually be equal to your B0. So how do you do your B0 cross R0E? So this is a column vector, this is another column vector. So for your theta 2, you do the same. Your JL2 will be actually equal to B1 cross R1E. JA2 will be B1. So you did the computation, did the calculations, this is what you have. T3 is a simple one. T3 is a prismatic joint. So your prismatic joint, your JL3 is equal to your BI minus 1 is your B2. And then the angular rotation part is actually equal to 0. So if I do a cross product, I'll do 3 by 3 vector. So A1, A2, A3, B1, B2, P3. So for the first row, the first row is essentially equal to A2 multiplied by B3 minus A3 multiplied by B2. The second row will be your A1 multiplied by B3 minus A3 multiplied by B1. And then and then you put a minus over here. And then for the third row, you will be A1 multiplied by B2 minus A2 multiplied by B2. So this is for column vector. So for example, if I have my B1 equal to minus x1, C1, 0, B2 equal to C1, x1, x1, x2, C2, my D3, B2 is straightforward. So the D3 is a scalar, so you multiply with the B2, so you have your D3, x1, C1, D3, x1, x2, D3, C2. So this is straightforward. And then when you have your B1 cross D3, B3, so meaning that you need to remember this IJK. So you take this one. For the I row, you'll be taking this one minus this one. This one multiply this one minus this one multiply this one, which is end up C1, D3, C2. Okay. So most of the time, we do a cross product of two row vector. But in our case, the position vectors are actually represented as a column vector. So you do the multiplication itself, you will actually end up with this. Then after that, you simplify. You do a simplification, and then you actually end up with the B1 cross D3, B3 equal to D3, C1, C2, D3, X1, C2 minus D3, X2. Okay. So you can go back and try it out. The dot product of the two column vector are straightforward. So your A1, A2, A3, B1, B2, B3 will still be equal to A1 times B1, A2 times B2, plus A2, B2 plus A3, B3. So the cross product of two column vector is probably something that we don't do that much in high school. Okay? Any question? The class is very quiet. Yeah. Okay. So this is how we end up with this one, with this vector. And then for the prismatic joint itself, it's straightforward. So you basically just take the B2, and then you pick up the B2 from the transformation matrix. So after this is done, you put all of them together. So this is your JL1, this is your JA1, this is your JL2, this is your JA2, this is your JL3, this is your JA3. Okay? You put all of them together, you have this single Jacobian matrix. So with this Jacobian matrix, you will be able to determine the end velocity based on the joint velocity, and then you can actually do it in a reverse manner also. You can also do it in the reverse manner if the matrix is not singular. Okay? If you can find the J minus 1. J invert. So look at the inverse instantaneous kinematics. So if I have a 6 degree of freedom manipulator, so from earlier we have P dot equal to JQ dot. The J is a 6 by 6 square matrix. If J is not singular, then your Q dot is equal to J minus 1 P dot. Then you can actually determine the joint velocity based on your n effector velocity. So you can actually determine the individual joint velocity to obtain a given n effector velocity. So this is the reverse. The inverse process. So the control scheme to generate the n effector velocity based on this approach is known as the result motion rate control. So at singular configuration, J is not full rank. So it's not full when you have single, then J is not full rank. That means the column vector are linearly dependent. So it does not span the whole 6-dimensional vector space of P dot, and then J therefore cannot be inverse. What is full rank? So when we say a matrix is full rank, if we consider an m by n matrix and m is less than m, the m by n matrix have a full rank when its m rows are linearly independent. So when we say the rows are linearly independent, the rows vectors are linearly independent, meaning that the vector equation, the x1, b1 plus b2, x2 plus dot dot plus vk, xk, vk is actually equal to 0 if and only if x1 is equal to x2 is equal to xk is equal to 0. So this defines the relationship of linear independence. Okay, so if the m by n matrix, when your m is bigger than m, so you have full rank when the m rows are linearly independent. So if m is equal to m, the matrix have full rank regardless of whether the row, when either its row or the column are linearly independent. Okay? So when the manipulator Jacobian becomes singular, a finite Cartesian motion rate may correspond to an infinite joint motion rate. So the manipulator may not be movable, it may be immovable in certain direction even after a very large torque has been applied. So the manipulator is singular, which is also referred to as degenerated. So you can actually imagine your arm. So your arm is two revolute joint, and then when you fully extend your arm, you have a singular configurations. So if you look at, so if you consider this example, the 2 degree of freedom planar manipulator. So if we make an assumption that the length of each link is actually equal to 1, so it's simplified. So that means the L1 and L2 is equal to 1. So, and then endpoint velocity will actually denote by V is equal to Vx Vy transpose. So this is Vx Vy, it's a column vector consists of Vx Vy. So you want to find the joint velocity that produces the desired endpoint velocity. So it's a forward relationship. You have your V equal to J Q dot. So earlier on, we have determined that the J, the Jacobian matrix, is equal to minus L1 sine theta 1 minus L2 sine theta 1 plus theta 2, and so on. Since L1 and L2 is equal to 1, we have the Jacobian equal to minus sine theta 1 minus sine theta 1 plus 2, and so on. So you have this, you end up with this Jacobian matrix. So the inverse of this Jacobian matrix, to determine the inverse, will be 1 over determinant. So you have 1 over determinant multiplied by this cofactor matrix. So this is how you determine the inverse of a matrix. So you have your 1 determinant of J. So you calculate the determinant of J. So this one minus this one multiply this one minus this one multiply this one. You have your sine theta 2. And after that, this is the cofactor. So the cofactor is essentially you have minus of this, and then you invert and then you exchange these two, and then you exchange these two elements. So you have this cofactor. This is your J invert. Okay. So your Q dot equal to J invert V will be your your Q dot, your theta dot consists of your theta 1 dot, theta 2 dot is equal to your J invert. This is your J invert multiplied by your Vx Vy. So you did the multiplication itself, you will find that your theta 1 dot is equal to this Vx cosine theta 1 plus theta 2 plus Vy sine theta 1 plus theta 2 divided by sine theta 2. So from here you can determine that we can when you are given the n effector, when you are given the n effector velocity. So in this case, you're given the n effector velocity, you can actually determine the joint the joint velocity with the J inverse. So we want to determine all the singular configuration. A singular configuration meaning that where you have your J where J is not full rank. You don't have your J minus 1. You don't have the J inverse. So the singularity will you don't have J inverse when your determinant of J is actually equal to 0. So your determinant of J, so this is the determinant of J is equal to 0. So 1 over 0 is infinite. So determinant of J equal to 0. The determinant J meaning that your sine theta 2 is actually equal to 0. So your theta 2 either have a value of 0 or pi. So when your theta 2 is actually equal to 0 or pi, you will have a singular configuration. So the singularity is actually determined only by theta 2. Okay, so the theta 1 doesn't play an effect over here, based on this from the analysis over here. Okay. So when you have theta 2 is equal to 0 or pi, so meaning that your arm, so this manipulator arm is either fully extended or fully contracted. So it's either when you have fully extended, so this is fully extended, the one in red is a fully extended, and the one in blue is a fully contracted. So when you actually either of this condition, you have a singular configuration. So the endpoint is either at the origin 0, when you, for example, look at the blue one, or either at the boundary of the reachable space. So at these two configuration, you will have singular configurations. So your determinant J is actually equal to 0. So a singular configuration with corresponding to theta 2 is equal to 0. So meaning that you have a fully extended one. So you do your J, this is your Jacobian matrix. Your theta 2 is actually equal to 0. Your J is equal to minus 2 sine theta 1 minus sine theta 1, 2 cosine theta 1 cosine theta 1. The theta 2 is actually equal to 0. So your Vx, Vy is equal to this multiplied by theta 1 dot and this multiplied by theta 2 dot. So you actually end up with this. Minus sine theta 1 cosine theta 1 multiplied by 2 theta 1 plus 2 theta 1 dot plus theta 2 dot. Okay? This is one singular configuration. So if you actually look at this, you can actually observe that the two columns of the Jacobian matrix become parallel. So the endpoint can only move in the direction perpendicular to the arm length. So these two columns are parallel. Okay? And then what happened? Okay. So you can do the same when you actually have your theta 2 equal to pi and then work out. And then work it out. So if you want to find the profile of the joint velocity when the endpoint is required to check the trajectory A, B, C, D. So for example, over here, you want your arm to follow a certain trajectory, A, B, C, D. So this is A, B, C, and D. You want your arm to from the fully extended position, then you pull it back. So from here you pull it back, and then to B, and then after that you rotate it to C, and then after that you extend it to D. So for example, you plan to program your planner robot to follow this trajectory, A, B, C, and D. So and then you want it to be done at a constant tangent speed. So you want to actually achieve it as a constant speed. So you need to find the joint angle that corresponds to each endpoint position on trajectory. So you do a calculation, you do the computation itself, and then you plot the theta I dot with the theta I dot with time. So you actually see the profile given over here. Okay. So it's quite interesting. So this is at point A. So at point A, you want a certain speed. So the joint, this is your joint theta 1 speed. The solid line is a joint theta 1. So the broken line is a joint theta 2. Theta 2 dot. This is the speed. So you have both speed moving down. And then when you come to B, so you can see the speed profile of the theta 1 and theta 2. So you need to coordinate the joint speed of theta 1 and theta 2. And after that you have your C. So this is the profile of C. And then you have your D. So you have something that is actually interesting. You have an interesting phenomena over here. So the both joint velocity near the singular point A and D are exceptionally large. So the joint velocity at these two singular points are exceptionally large. So the denominator are almost zero. And then the first joint velocity become excessively large, become between B and C. So this one theta 1 dot actually become very large. So it actually tells you that even if the inverse of a manipulator Jacobian exists, the joint velocity may become excessively large in the vicinity of a singular point. So at the singular point itself, you can have very large speed. So therefore, it's important to address singularity and actually determine how to actually avoid them. So when we actually look at this, when we actually look at the Jacobian, then the other thing that we actually that we want to is deal with the Jacobian metric, the manipulator itself, is deal with the workspace, like what we have gone through earlier, and then the other thing that we're actually looking at will be the redundancy. So the redundancy in robotics will actually simply imply that there are more than one solution to the inverse kinematic equations. So this is redundancy. So we assume that the n factor have 6 independent variables. So if the manipulator arm have exactly 6 degrees of freedom, the kinematic equation will give you a finite number of solutions. The instantaneous kinematic equation will give you a unique solution. So meaning that a unique solution will exist when the arm configuration is non-singular. So we are looking at one that have exactly 6 degrees of freedom. Our human arm has 7 degrees of freedom. So our human arm is have redundancy. So when your manipulator arm having 6 degrees of freedom, having more than 6 degrees of freedom, for example, our human arm. So in this case, we're actually excluding the finger joints. So there will be an infinite number of solutions for the kinematic equations. And then the instantaneous kinematic equation will have infinite number of solutions. So if I have a general m degree of freedom manipulator, you're given a specific task. You need to specify the m independent variable. So you have your dp equal to dp1 to dpm transpose for the n effector when m is less than or equal to 6. So for example, the arc welding, so 5 independent variable of touch motion need to be specified due to symmetric about the center line. So if your instantaneous kinematic equation for the n degree of freedom robotics in general file form will be given over here, where you have your dp, which is a m by 1 vector, is equal to your Jacobian matrix m by n multiplied by your dq, which is m by 1. So the m over here actually indicates the number of joints. So when your m is greater than m and j is full rank, the question is how many redundant degree of freedom for the given task. So this is the definition of full rank. We have talked about the full rank before. So if it's a full row rank, meaning that each of the rows of the matrix are linearly independent. And full column rank when each of the column of the matrix are linearly independent. So when you have m greater than m, so it's the m. So if you have full rank when you have your m vectors being linearly independent. So altogether, you have m minus n redundant degree of freedom for the given task. So therefore, the m minus n redundant degree of freedom will actually imply that there will be m minus m arbitrary variable in the general solution of the instantaneous kinematic equation. Okay. So we study the Jacobian. We study the redundancy with the mapping with the mapping diagram. So you know that the Jacobian metric will determine the relationship between the n effector velocity p dot and the joint velocity q dot. So you have your p dot equal to j q dot. So when you look at this equation itself, it's actually imply a linear mapping from the m-dimensional vector space Vm to m-dimensional vector space Vm. So you have your q dot belong to the set of Vn, and q dot and p dot belong to the set of Vm. So this is the Jacobian matrix. So when we talk about the dimension of vector space, we actually refer to the number of vectors in every basis. So a basis is a set of vectors that have two properties. The vector are linearly independent, and then the vector actually span the vector space. In our context, you know that the p dot over here refer to here, the q dot over here refer to the joint. So this is the joint space, this is the n effector space. Okay, your p dot and q dot. So this is the mapping diagram. So the Jacobian will actually map the q dot to the p to a range space at the p dot. So this is known as the range space. So this color space is actually known as the range space, which is your Rj. So this Rj implies all the possible n effector velocity at the given manipulator posture. So that means all your joint configurations, the speed of the velocity of your joint at this space will only be mapped to a subset of your p dot. Okay, so there's actually a space that's actually not being covered. So the space that's actually been mapped onto is known as the range space. And this diagram is actually known as the linear mapping diagram. So the subspace, the Nj, is a null space of the linear mapping. So what is a null space? So this null space at the null space, your JQ dot is actually equal to 0. So meaning that at this particular space, it will actually project to a spot where your P dot is actually equal to 0. So another way of looking at it, meaning that your any joint velocity that actually belong to this pink area, meaning that belong to the null space, will not produce any velocity at the n effector. Follow? So for example, you can imagine your human arm. So you put your human arm. You can move your human arm without actually moving the hand. So for example, you hold your hand, and then you hold your hand in position, and then I will in position, and then I actually move the arm. So my n effector is actually not moving, but my lower arm is actually moving. Yeah. So for example, you can also do this example when you actually put your hand, and then you turn around. So this is, your n effector is not moving. Okay, so this is the null space. So what exactly is a subspace? So if V is a subspace over a field K, a set of real number, and then we let W be a subspace of B, then W is a subspace if only if it's actually satisfied these three conditions. So the zero vector is in W, and U and V, and if U and V are elements of W, then the sum U and V is also an element of W. And then if U is an element of W and C is a scalar form K, then the scalar product CU is an element of W. So the theorem actually implies a linear systems. So what happens is if we assume the M is greater than or equal than M. So meaning that you have your number of joints more than the task, more than the requirement of the task. So if your J is of full rank, of full row rank, your range space will actually cover the entire VM. So meaning that your Q dot M, which is the space over here, will come to 0. The entire Q dot M, the Jacobian will actually map to the entire n effector space. Okay. So any point over here will have a correspondent with your P dot. So when your M is equal to M, or M is greater or equal to M. So your number of joints is actually more than the requirement of the task. Okay. If J is degenerated, so meaning that singular, so your dimension of Rj will actually decrease. This is your dimension of Rj will actually decrease, and the dimension of Nj will actually be increased. So that means there's actually more, your null space will actually be increased. So remember, the null space is always projected onto the point where your P dot is actually equal to 0. But your dimension of the Rj plus the dimension of Nj will always be equal to n. And this will hold independent of the rank of J. What happens if Mj is not an empty set? So that means there's a solution. So this is not equal to empty. The null space is not equal to empty. Your Q dot star is a solution. Will be, and you assume that the Q dot star is a solution of your equation 4-3. So So equation 4-3. Okay, equation 4-3, your P dot equal to J Q dot. Then your Q dot J will belong to the set of Nj. So your Q dot is equal to Q dot star plus K Q0 dot. So it's also a solution of the equation 4-3. So K is a scalar constant. When you actually expand out itself, you will actually find that the JQ dot is equal to P dot. So you can use the redundancy to avoid a singular point and for optimal motion control. So it's good to have redundancy. So meaning that you have a robot that actually have more degree of freedom, more than the task require. Okay, please bear with me a bit more on this optimal solution. Yeah. So if you assume m is greater than m, so that means there's a redundancy. So earlier on we put m is greater or equal to m, so meaning that there's still a possibility that you have the degree of freedom equal to the task required. So now you have redundancy, and J is of full row rank, so meaning that you can actually find your J inverse. So you want to find your Q dot that satisfies the equation P dot is equal to Q dot is equal to P dot is equal to J Q dot. Then you can minimize a cost function. So this is the cost functions, and the W over here is a symmetric positive definite weighting metric. And then the method to solve this problem will be using something called a Lagrange multiplier. So you can, with the Lagrange multiplier, you can modify the cost function over here. So the necessary condition for the optimal solution will be your delta E divided by delta Q dot equal to 0. So that means it's a minimum or maximum point. So at your minimum or maximum point where you have your partial differential equal to 0, so you do the partial differentiations, you have these 2W Q dot minus J transpose lambda is equal to 0. Your Q dot is equal to half W inverse J transpose lambda. So we're not going to do the deviations. And then if you do the partial differentiation of E with lambda, so you have your equal to 0, your J Q dot minus P dot is actually equal to 0. So you can actually determine your lambda to be equal to this. So we say that this matrix is a full rank square matrix, is inversible because J is actually assumed to be a full row rank. So you can actually determine your, so this is a full rank square matrix. But what happens is M by N identity matrix. So identity matrix 1, 1, 1, 1, 1, remember? Yeah, 1, 1, 1 at the diagonal. So it's your identity matrix. So your Q dot is equal to J transpose. So this is your identity matrix. The inverse of your identity matrix will still be an identity matrix. So anything multiplied by identity matrix will be itself. So you have your, so this one can be taken out. So you have your J transpose invert P dot. So this is known as the pseudo inverse of J. So it's a hard problem for the computations of manipulated Jopopian for real-time control. So you have to consider the singularity as well as the redundancy. I think we have enough for today. So, yeah. So next week will be our last lecture. I don't think I don't think there's a need for a makeup lecture during the recess week. So I'll complete the section 3 for chapter 2 as well as chapter 3 on the trajectory planning. So have a good night. Can I see the members of CA Group 3 and CA Group 31? Are you here? CA Group 3? Yes.
I have a question for chapter 1. When we are attaching the frame to the link, I also that there is a distance between the link and the XI axis. Does it really matter? Because it's not specified here.
Yeah, it doesn't matter. So,
okay.
for the matrix itself, we just need to worry. Oh, sorry.